All right, let's jump right in. In electronics, we spend so much time talking about gain, how to make a tiny signal bigger. But what happens at the very end of the chain? That's a whole different ballgame. We're not just trying to make a signal bigger anymore. We need to make it powerful enough to do real work, like, moving the cones in a speaker or pushing a signal out of an antenna.
Yeah, exactly. We know how to make signals bigger, but how do we make them strong? It's not just about voltage anymore. Now we have to think about current, too. This is the muscle of the whole system. And what's so cool about this is that building that muscle, well, it's all about making some really tough choices. You'll see it's a constant battle between how clean the signal is, how much power you're wasting, and just pure raw output.
So let's talk about the mission, delivering power. Our goal is simple, right? Take a nice big signal and get it to a load, like your headphones, without messing it up and without wasting a ton of energy. And because we're playing with the big stuff now, high currents and high voltages, all those simple little models we're used to, they kind of go out the window. We've got to approach this in a whole new way.
Okay, so how do we even begin to categorize all of these different designs? Well, it's pretty wild, but it all boils down to this one simple idea, the conduction angle. All that means is, if you look at one full cycle of an audio wave, what percentage of that time is the transistor actually on and doing work? It sounds simple, but that one number, that angle, tells you almost everything you need to know about how an amp is going to behave, how efficient it is, and how clean it sounds.
All right, first up, let's talk about Class A. This is the simplest, most obvious way to build a power amplifier. It's the gold standard for purity and fidelity, the audiophile's dream. But that perfection comes with a huge catch.
The idea behind Class A is super simple. The transistor, it's on, all the time. For the entire 360-degree swing of the signal, it's conducting current, never taking a break. What that gives you is a perfect mirror image of the input signal at the output. It's incredibly linear, super clean, no distortion. I mean, what could be better than that, right? Well, about that. Here's the killer, 25%. That's its maximum theoretical efficiency. Let that sink in. For every 4 watts of electricity you feed this thing, only 1 watt actually becomes sound. The other 3, they're just turned into heat. That's why those fancy Class A audiophile amps can literally double as space heaters. They're just incredibly wasteful.
Okay, so clearly, engineers had to come up with something better, and that brings us to Class B. This design was born from one single mission: fix the insane inefficiency of Class A. It's a much more clever design, but in solving one problem, it created a totally new one.
And wow, what an improvement. Just look at that jump in efficiency, from a measly 25% all the way up to a theoretical 78.5%. That's a game changer. And the way it works is really smart. It's a push-pull setup. You have one transistor that handles the top half of the wave, the positive part. And then it turns off, and a second transistor kicks in to handle the bottom, negative part. Since they're each only working half the time, you save a massive amount of energy. But there's always a but, isn't there? That handoff from the push transistor to the pull transistor, it's not seamless. Right at that zero crossing point, where one stops and the other starts, you get this nasty little glitch. And it has a name: crossover distortion.
So, what's actually going on? Well, for a tiny moment, right as the segment crosses zero, neither transistor is on. It's like dropping the baton in a relay race. You get this dead band. And even though it's super short, you can hear it. In music, it sounds kind of grainy and harsh. So, great. We solved the efficiency problem, but now our beautiful clean signal is all messed up.
So, let's recap. Class A, pure sound, terrible efficiency. Class B, great efficiency, ugly distortion. You can probably see where this is going, right? We need a compromise. And that perfect middle ground is Class AB, the design that basically powers most of the high-quality audio gear you see today.
And the fix is actually genius in its simplicity. So, the problem is that dead band where both transistors are off. The solution? We just apply a tiny little voltage to both transistors to keep them barely on all the time, just idling. The result? Now, instead of one turning off completely before the other turns on, there's a tiny bit of overlap. They're both on for just a hair over 180 degrees, and that ensures a perfectly smooth handoff. Dead band gone, problem solved.
Now, getting that tiny little bias voltage just right is absolutely critical. And for that, engineers use this fantastic little circuit called a VBE multiplier. It's the secret sauce. Not only does it create that perfect bias voltage, but it also does something else that's incredibly important. It helps with temperature. It prevents a terrifying thing called thermal runaway, which is this vicious cycle where the amp gets hot, which makes it draw more current, which makes it get even hotter, until, poof, it literally destroys itself. Okay, so far we've been talking about evolving an idea from A to B to AB. But now, let's just throw all that out. Let's talk about Class D. This isn't just the next step, it's a complete revolution. It's a totally different way of thinking about amplification. And this right here is the key, the big idea. All the other amps we talked about, they treat the transistor like a faucet or a dimmer switch, a variable resistor, and that always wastes energy as heat. But Class D, it says forget that. Let's use the transistor as a simple on-off switch. It's either fully on or fully off, nothing in between. This is really the best way to think about it. A Class A or AB amp is like that old dimmer switch on your wall. To make the light half bright, it has to burn off half the power as heat. It's so wasteful. A Class D amp, on the other hand, is like a super fast strobe light. It's only ever fully on or fully off, wasting almost no energy. So how do you get different brightness levels? You just change how long the on flashes are compared to the off flashes. That's called pulse width modulation. And because it's so incredibly efficient, like close to 100%, it's the reason your tiny little smartphone can be so loud without melting.
Okay, this all sounds great in theory, but making this stuff work in the real world, that's where things get tricky. When you're dealing with a lot of power, no matter what class of amplifier you're building, you run into some very real, very physical problems that you have to solve to keep things from, blowing up.
You've really got three main enemies. First is just heat. Any wasted power has to go somewhere, and you need big chunks of metal, heat sinks, to get it away from your sensitive components. Second, that scary thermal runaway we talked about, it's always lurking, ready to wreck your day. And third, you need protection against short circuits. Think about it. If your speaker wires accidentally touch, the amp will try to pump out basically unlimited current, and it will fry itself in a split second if you don't have safety circuits built in.
So that kind of brings us full circle. The next time you put your hand on your stereo receiver and feel it's warm, that's not just a random thing. That heat is a clue. It's the physical evidence of the design choices the engineers made. It's the story of that constant trade-off between perfect, pure sound and raw, efficient power. So you have to ask yourself, is that warmth just wasted energy, or is it the necessary price for getting perfect sound?